Greetings and welcome to my channel. I am Mr. D, and today we'll be discussing the periodic table. We'll talk a little bit about its historical development, how it's arranged, why it's arranged that way, and how to navigate it, and what information we can learn from it. As more and more elements were discovered, it became apparent that there were similar properties between some of these elements. While noted early on, the significance of this fact was not immediately recognized. In 1829, Dobryner attempted to bring some order to the growing number of elements. He grouped several of the elements into groups of threes that he called triads based upon these similarities. Most chemists dismissed his work as amusing but unimportant. Since there didn't seem to be much utility to this, it didn't go anywhere, but it did hint at a way to bring order to the chaos. Newlands in 1865 took things a step further. He arranged the known elements in order by increasing atomic mass, and when he did, he noticed that there was a repeating pattern of properties every eighth element. Based on this, he grouped the elements into 7 groups of 7 and he called them octaves. Per his law of octaves, when elements are arranged in order of increasing atomic mass, every eighth element has similar properties, and where it went wrong was that he had forced some of these elements into columns that didn't belong to, so he could have his nice, neat columns. So he had elements with dissimilar properties grouped together, and there were elements being found that didn't fit. Opponents of his attempt said what he had done would have been just as useful as if he had arranged the elements alphabetically. His work was initially met with disapproval, but it set the stage for the work to come. In 1869, Russian chemist Dmitry Mendeleev was writing a chemistry textbook to use with his classes. As part of his effort, he wanted to bring order to the elements. Like Newlands, he started out by arranging the elements in the order of increasing atomic mass. Where he differed was that he left elements' properties guide him to placement in those columns. As a result, he ended up with columns of varying lengths. And when he got to iodine and tellurium, he discovered that if he went strictly by atomic mass, these two elements would end up in columns where they didn't belong based upon the properties. So he ignored the inconsistency and placed them into the proper columns based upon their properties, making the erroneous assumption that the mass of one or the other elements had been miscalculated. It turned out that this wasn't the case, but it was okay, as you'll see shortly. More importantly, Mendeleev left gaps in his periodic table for elements that he felt hadn't been discovered yet. Further, using his periodic table, he looked at the elements above and below the gaps and to the left and right of them, and used the information there to predict the missing elements' atomic masses and several other characteristics. Western scientists were unimpressed by this, chalking it up to Russian mysticism. Mendeleev was vindicated when the predicted elements were discovered: gallium in 1875, scandium in 1879, and germanium in 1886. He and his table won universal recognition. His work earned him the title of the father of the modern periodic table. It was Moseley's work in 1910 on atomic numbers, which was the final key to unlocking the usefulness of the periodic table. Prior to using atomic number to arrange the elements on the periodic table as we do today, in order for Mendeleev's table to work for every element, a little finagling was sometimes necessary. If you recall back to the earlier comments about iodine and tellurium. If it went strictly by atomic mass, Mendeleev wouldn't have been able to put those elements with similar properties together. In addition to these two elements, other anomalies had occurred. Pairs of elements that didn't fit in this situation were argon and potassium, and nickel and cobalt. If most of these atomic numbers were used instead of their atomic masses, then the finagling wasn't necessary. Let's look at the boxes in the periodic table. Not every periodic table has these things arranged in the exact same way, and some include more information than others. We'll be using the periodic table that I have linked to in the description below for our discussion today. The number in the upper left-hand corner will be the atomic number. The 1 or 2 letters in the middle of the box are the symbol for the element, and below the symbol is the element's name. The number at the bottom of the box is the average atomic mass for the element. If the number is in brackets, then that means that there's no stable isotope for that element, and the mass that is given is the mass of the isotope with the longest half-life. Most of the elements on our periodic table here are in blue shaded boxes, and these are the metals. The elements in the green shaded boxes on the right are the nonmetals, and the elements in the blue-green shaded boxes between them are the metalloids. A metalloid is an element that has properties of both metals and nonmetals. So for instance, it may be shiny like a metal, but be brittle. So if you hit it with a hammer, instead of denting or getting squished like a metal, it shatters into little pieces. You can also tell what phase the element will be in as standard temperature and pressure by the color of the symbol. Red is gas, blue is liquid, black is solid. Gray indicates that the phase is unknown because these elements are synthetic or man-made, and as such are unstable and only exist for a short period of time in very small quantities. You'll note two sets of elements that have been pulled out of the main body of the periodic table and placed below it. This is done merely for the sake of convenience. If they're placed in the middle of the periodic table where they belong, the table would be somewhat unwieldy and not readily fit on a page in a readable fashion. It would make for especially large wall charts. You'll notice this first row here is labeled the lanthanide series, and that's because it follows right up after lanthanum. It fits in here between lanthanum and hafnium, so you just cut a line right here and push all of this over. The second row here is the actinide series, so it fits right here after actinium, between actinium and rutherfordium. The main body of the periodic table can be labeled as columns 1 through 18. These vertical columns can also be divided into group A elements, known as the representative elements. Please note that the group number is a Roman numeral followed by a capital letter, and the number will correspond to the number of valence electrons. The group B elements are known as the transition metals for the 10 columns in the middle of the periodic table, main body of the periodic table, and then the inner transition elements for the 28 elements at the bottom of the table. You'll sometimes see these elements referred to as the rare earth elements. That's because at one time it was thought that these elements were actually pretty rare. It turns out that for the most part they're about as abundant as other metals like nickel and copper, but they're difficult to separate from the ores in which they're found, so it made them appear to be rare. You'll notice that the atomic masses for all the elements after uranium are in brackets. These elements, sometimes called the transuranium elements, are all radioactive. And elements that have the elements in brackets shows that there's an element that has no stable isotopes. The mass number of the isotope with the longest half-life is the number that they choose to use for the atomic mass for that isotope. Some of the columns of the representative elements have long-standing names that are still used to some extent today. The family name for group 1A is the alkali metals. They are called this because their metals and their oxides, when reacted with water, produce basic or alkaline solutions. They are soft, silvery metals that are very active. As such, you will only find them as compounds in nature, never in their elemental state. This is because they only have one valence electron, which they will give away very readily when they react. The group 2A elements are known as the alkaline earth metals. As with the alkali metals, these metals and their oxides react with water to form basic solutions. The word earth in the name comes from the fact that oxides of group 2A metals were at one time called earths. They are also soft silvery metals that are active. They aren't as active as group 1A, but they're still pretty active. And like group 1A metals, you won't find them in their elemental state in nature. This is because they only have 2 valence electrons, which they easily donate when reacting. The next couple of columns don't really have family names that are used anymore. I just wanted to kind of point out some things real quick. Boron and aluminum, when they form compounds, tend to have a 3+ charge because they will lose 3 valence electrons. The other elements, the charge can vary a little bit, and we can talk about that probably in another video down the road. Carbon and silicon tend to form 4 bonds, but carbon specifically forms what are known as covalent bonds. They share electrons instead of losing or gaining them. So they have 4. They're in group 4A, so they have 4 valence electrons already. They form 4 bonds, so they get a total of 8, and that gives them that filled valence shell of 8 valence electrons. Tin and lead can form more than one type of metal ion. So again, we'll talk about that at another time. Group 5A, non-metals here, nitrogen and phosphorus will form a 3- charge, because these, since they have 5 valence electrons, only need 3 more electrons to get a filled valence shell. So they tend to gain electrons, giving him gaining 3 valence electrons, giving him a 3- charge. Oxygen, group 6A, oxygen and sulfur tend to gain 2 electrons, so they get a 2- charge. Our next family here, our next group, has the family name of the halogens. Group 7A is known as the halogen family, and they're named this way because they form halides or salts when they react with the group 1A, 2A metals, halogen being translated as salt maker. They're very active nonmetals and only found as parts of compounds in nature. They are so reactive because they have 7 valence electrons and only need 1 more to have a filled valence shell. So they're very eager to react to gain this electron. Fluorine and chlorine are the 2 most active nonmetals. Our last group here is the noble gases, and they're shaded in pink on our periodic table. Initially, they were referred to as inert gases because they were believed to be inert or unreactive and didn't form compounds. It has since been found that with a little chemical arm twisting, through the use of catalysts and some very active elements, that some of these gases can be made to form compounds. As a result, a name change was needed. Since these gases are like the nobility in society, who tend not to interact with the more common folk, or in our case, elements on the periodic table, the name noble gas has been bestowed on this last column of elements. The reason they're so unreactive is because their valence shells are filled, they're complete. They neither want to lose nor gain electrons. The periodic table has 7 horizontal rows, or periods, keeping in mind that the 28 elements at the bottom of the table are parts of rows 6 and 7. The period numbers will correspond to the number of energy levels that atoms of those elements will have. There's a few items of note that I wanted to point out. First, you'll probably notice that I have hydrogen, which is a nonmetal, in the far left with the group 1A metals, because this is because, chemically speaking, it can behave like a metal, much like the rest of the column. Group 1A, it only has 1 valence electron. Many periodic tables will actually bump hydrogen up from the rest of the group 1A as a way of notating that it's different from those elements. Next, you'll notice that there's an element in the middle of the periodic table that is radioactive. The element I'm referring to here is number 43, technetium. Technetium was actually synthesized before it was found in nature. It was created in the lab in 1937 and then found in the spectra of red giant stars in 1952. As a result of the lack of a stable isotope, it'll appear on some periodic tables as it isn't naturally occurring, but rest assured that it is. This is also the case with promethium, number 61, and astatine, number 85. They too are naturally occurring, but all their isotopes are radioactive. These 3 elements are present in Earth's crust in extremely small quantities. We're talking mere grams at any given moment. These radioactive elements have relatively short half-lives, which is how the length of time that it takes for radioactive decay to occur is measured. They only occasionally are created during the radioactive decay of other elements. The half-life for technetium is 10 million years, a short time geologically speaking, and astatine is only 18 years. Now that you know how the periodic table works, let's see if you can find a few elements based upon a few facts that I will give you. I'll give you the clues to find the elements and then wait a few seconds for you to find them, and then give you the correct answer. Ready? Here we go. What element has 3 valence electrons in its 3rd energy level? Hopefully you said aluminum. We said it has 3 valence electrons, so we know that it's going to be in group 3A. And we said those valence electrons are in the 3rd energy level, so it means it's going to be in the 3rd period. What element has a filled valence shell, which is the fifth one, and it holds 6 electrons? So its valence shell is the fifth one, so we're looking for period 5. 1, 2, 3, 4, 5. And we're looking for it to hold 6 electrons. So we're looking for group 6A. So we're talking about tellurium. What metalloid in period 4 has 4 valence electrons? So we're looking for period 4. 1, 2, 3, 4. And we're looking for a metalloid, so it's going to be one of these two here. And we said it has 4 valence electrons, so it's going to be in group 4A. So that means it's going to be germanium. What is the only liquid nonmetal? And as you can see, bromine is the only nonmetal that's printed in blue, has a symbol printed in blues, so it is a liquid. What is the only liquid metal? And again, the symbol for mercury is printed in blue. So mercury meaning that mercury is a liquid metal. What noble gas has no stable isotopes? So we're looking for a noble gas. So we're looking at the far right, the pink elements, or the elements in the pink boxes. And we're looking for one that has no stable isotopes. So that means its atomic mass is going to be in brackets. And the only one that fits that case is radon. What group has 2 nonmetals, 2 metalloids, and 1 metal? And that's going to be group 5A. 2 nonmetals, 2 metalloids, and 1 metal. These elements down here, they've not been really indicated what class of element they're going to be. They're probably going to be metals, but it's never been actually given. So that's why they're white like this. As you look from left to right, what's the first column that you come to with the metalloid in it? Hopefully that's a pretty easy one. Going from left to right, looking for the first time you hit a blue-green element, and that's going to be column 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In what group will you find an element with 56 protons? So you want 56 protons, so you're looking for atomic number 56. And that's going to be barium. So that means it's going to be in group 2A. In what row will you find a very active gaseous nonmetal between a noble gas and a solid nonmetal? Okay, so we're talking about the nonmetals. So we're over here in the green elements. We're looking for a very active gaseous nonmetal. So very active nonmetal are going to be the halogens. It's gaseous, so it's going to be in red. So it's one of these two here. And it's between a noble gas and a solid nonmetal. So the one that fits the bill here is going to be chlorine. So that's going to be in period number 3. Last one. In what period will you find a solid nonmetal flanked by 2 nonmetals on one side and 2 metalloids on the other? And that's going to be period 4. You've got 2 you got a solid nonmetal, selenium, flanked by 2 metalloids and two nonmetals. Biographical endnote. Dmitry Mendeleev was born in Siberia in 1834. He was the youngest child of a family of around 15 children. His father was a principal of the local high school, but while Dmitry was still young, he had to resign due to his health issues. His disability pension wasn't enough to support the family, so his mother reopened a derelict glass factory owned by her brother and successfully ran it and managed to make ends meet. In 1849, as he was graduating from high school, his father died and the glass factory burned down. Since her older children had all been settled, his mother devoted her energy into continuing his education. They went to Moscow to try to get him into the college, and were unsuccessful. They then traveled to St. Petersburg, where a friend of his father used his influence to get him into school there. Shortly after accomplishing her goal, his mother died. In 1855, he graduated at the top of his class and traveled to France and Germany to continue his education in chemistry, as there were no universities in Russia that were able to provide him with his advanced education that he sought. He returned to St. Petersburg in 1866 and became a professor at the university there. He was the most interesting lecturer in Russia and one of the best in all of Europe. It was because of him that students wouldn't have to leave Russia as he did in order to get advanced training in chemistry. In 1867, the university appointed him professor of general chemistry. He was required to lecture on inorganic chemistry, and since there was no satisfactory Russian textbook, he began writing one. It was during this time that he did his groundbreaking work on the periodic table that we discussed earlier. He became the most famous scientist in the world and was honored in 1882 with a Davy Medal by the Royal Society in Britain. Mendeleev was unconventional in his private life as well as he was in his professional one. He had his hair cut and beard trimmed only once a year, choosing not to vary from this even for an audience with the Tsar. He spoke out against oppression of his students without fear, even though he had been scolded multiple times and missed out being elected to the Imperial Academy of Sciences. In 1890, he finally resigned his position at the university over the oppression of his students. In 1955, the newly discovered element 101 was named in his honor. Thank you for watching my video today. I hope you found it both informative and interesting. If you did, please smash that like button below and consider subscribing and hitting the notification bell so you know when my next video comes out. When it does, please join me again. Until then, be good, be careful, and don't trust atoms. They make up things.